Welcome to this coding walkthrough. Today, we'll be diving into problem number 3, longest substring without repeating characters. This is a classic problem that tests your ability to work with strings and optimize for performance. Stick around as we explore some interesting approaches to solving it. In this problem, we are tasked with finding the length of the longest substring in a given string S where no characters are repeated. The input to the problem is a single string S with a length of n, and the output is an integer representing the length of the desired substring. For example, if the input string is S equals abcab, the output will be 3. This is because the longest substring without repeating characters is ABC, which has a length of 3. To understand this better, let's look at the explanation for the first example. The string S equals abcab contains repeating patterns, but the substring ABC does not repeat any characters and has a length of 3, making it the longest valid substring. For the second example, where S equals BBBBB, the output is 1 because all the characters are B, and the longest substring without repetition is just a single B. Now, for the third example, consider the input S equals PQ. In this case, the output is 3. The substring YK is the longest substring without any repeating characters, and its length is 3. While the substring PQ might seem longer, it includes the repeated character P, which makes it invalid. Finally, for the fourth example, if the input is an empty string S equals, the output is 0 because there are no characters in the string to form a substring. There are a few important constraints and edge cases to keep in mind. The length of the string S can range from 0 to 100,000, and S may include English letters, digits, symbols, and spaces. For edge cases, if the string is empty, the result is 0. If all characters are unique, like S equals ABCDEF, the result is simply the length of the string. Conversely, if all characters are identical, like S equals AAAAA, the result is 1. For strings that mix repeating and unique substrings, such as S equals abcab, the result is determined by the longest substring without repeated characters. To solve this problem, one of the first approaches we can consider is the brute force method. The intuition here is straightforward. We systematically explore all possible substrings of the input string and check if each substring is free of duplicate characters. This can be achieved by using a helper function or a data structure like a set, which allows us to verify the uniqueness of characters in a substring. The process involves generating substrings starting from each character in the string, validating each substring, and keeping track of the longest valid one. While this approach is conceptually simple and easy to implement, it is computationally expensive. Generating substrings takes quadratic time, and checking for duplicates within each substring adds another linear factor, leading to a time complexity of O(n cubed). Additionally, it uses extra space for storing characters in a set, making it impractical for larger inputs. This trade-off between simplicity and inefficiency makes it clear that we need a more optimized solution for this problem. An improvement over brute force is the sliding window approach, which is much more efficient. The idea here is to use 2 pointers to define a dynamic window over the string that expands and contracts as needed. As we expand the window by moving the end pointer, we check if the newly added character is already present in the current window, which is tracked using a set. If a duplicate is encountered, we adjust the start pointer by moving it forward and removing characters from the set until the duplicate is resolved. Throughout this process, we continuously track the maximum size of the window that contains only unique characters. This approach avoids the need to generate all substrings explicitly and instead focuses on maintaining a valid window, resulting in a linear time complexity of O(n). However, it does require careful management of the pointers and the set, which introduces some complexity. Still, this method is significantly more efficient than brute force and avoids redundant computations. To further optimize the sliding window approach, we can use a hash map instead of a set to store the last seen index of each character. This allows us to resolve duplicates more efficiently. Instead of removing characters one by one when a duplicate is encountered, we can directly jump the start pointer to the index just after the previous occurrence of the duplicate character. This eliminates unnecessary removals and ensures the window remains valid. The process involves iterating through the string with the end pointer while updating the hash map with the latest index of each character. If a duplicate is found and its index is within the current window, we adjust the start pointer accordingly. The maximum window size is then calculated as the difference between the end and start pointers plus 1. This optimized approach retains the linear time complexity of O, n, while reducing redundant operations, making it both efficient and practical. Although it is slightly more complex to implement than the basic sliding window, the performance benefits are significant. Given the options, we chose the optimized sliding window with hashmap approach as the most suitable strategy for solving this problem. The key insight here is recognizing that instead of incrementally removing characters, we can directly jump the start pointer using the hashmap, which minimizes redundant computations. This method is highly efficient, with a linear time complexity of O, n, and is well suited for handling large inputs. It also balances simplicity and performance, as the logic, while slightly more intricate than the basic sliding window, is intuitive once understood. Compared to the brute force approach, which is far too slow for practical use, and the basic sliding window, which involves unnecessary removals, the optimized version stands out as the most effective. By leveraging a hashmap for direct lookups and updates, and using 2 pointers for linear traversal, this strategy ensures optimal performance while maintaining clarity and robustness. Although the chosen strategy is slightly more complex to implement than the basic sliding window approach, the performance improvements it offers more than justify this trade-off. By directly jumping the start pointer to resolve duplicates, we eliminate unnecessary operations, making the solution both efficient and elegant. This method is particularly well suited for real-world scenarios, where handling large datasets efficiently is crucial. The optimized sliding window with hashmap strikes the perfect balance between simplicity and performance, providing a robust solution to the problem of finding the longest substring without repeating characters. Its linear time complexity and efficient use of space ensure that it can handle edge cases and large-scale inputs effectively, making it the most practical choice for this problem. The problem we're solving here is to find the length of the longest substring in a given string that contains only unique characters. A brute force approach to this problem involves examining every possible substring of the input string and checking each one to see if it has only unique characters. To implement this, we start by initializing a variable, max_length, to keep track of the longest unique substring we find. Using nested loops, we systematically generate all possible substrings. The outer loop iterates through each potential starting index of the substring, and the inner loop iterates through all possible ending indices for that starting point. For each combination, we extract the substring using slicing. This straightforward method ensures we don't miss any substrings, but it comes at a computational cost, as we'll see shortly. Once we have a substring, the next step is to check if all its characters are unique. This can be done using a helper function or a set. By adding each character of the substring to the set, we can efficiently detect duplicates. If a duplicate is found, we break out of the loop since the substring is no longer unique. If the substring is verified as unique and its length exceeds the current max_length, we update max_length. Finally, after examining all substrings, we return the value of max_length, which represents the length of the longest substring containing only unique characters. While this approach is conceptually simple and easy to implement, it is computationally expensive since it evaluates every possible substring. Analyzing the brute force approach, we see that its time complexity is quite high. Generating all substrings requires n² time, as we use nested loops. Checking the uniqueness of each substring introduces an additional m complexity, where m is the substring's length. In the worst case, this could be as high as n, resulting in an overall time complexity of n³. Space complexity is proportional to the size of the set used to check uniqueness, which is m. While this solution works for small strings, it becomes impractical for larger inputs. This inefficiency opens the door for optimization, such as avoiding redundant checks or leveraging techniques like the sliding window or hash map approaches to significantly reduce the complexity. To implement the brute force approach effectively, we rely on specific data structures. A set is crucial for ensuring all characters in a substring are unique. Operations like adding a character, checking for duplicates, or clearing the set are performed in constant or linear time. Additionally, string slicing is used to extract substrings from the input during iteration. While convenient, slicing has a time complexity of O(m), adding to the inefficiency of the brute force method. Let's look at a visual example. If the input string is s equals abcap, the outer loop starts with I equals 0, and the inner loop generates substrings like A, UB, and ABC. These are all unique, but when the substring abca is reached, the duplicate causes the process to halt for that iteration. At this point, max_length is updated to 3, reflecting the length of the longest unique substring found so far. Next, the outer loop moves to the starting index I equals 1. From here, the inner loop considers substrings like B, BC, and Ka. Again, these are evaluated for uniqueness, and max_length is updated if a longer unique substring is found. This process repeats for every starting index I in the string. Eventually, the algorithm determines that the longest substring with unique characters is ABC, with a length of 3. We also need to account for edge cases. For an empty string, there are no substrings to evaluate, so the output is 0. For a single character string, the output is 1 since the single character itself forms the longest unique substring. We also encounter other interesting scenarios. For a string where all characters are unique, such as A, B, C, D, E, F, the output equals the length of the string itself, as the entire string is unique. On the other hand, if all characters in the string are identical, like AAAA, the longest unique substring is just one character long, with a length of 1. To improve efficiency, we can use optimized approaches such as the sliding window or hash map. These methods maintain a dynamic window of unique characters, eliminating the need to repeatedly recalculate duplicate checks for overlapping substrings. By adopting these techniques, we can reduce the time complexity to O(n), making the solution far more scalable for larger inputs. This implementation efficiently solves the problem of finding the length of the longest substring without repeating characters using the sliding window technique. First, we initialize a dictionary char_index to keep track of the last seen index of each character in the input string s. The left pointer is initialized to 0 and represents the start of the current window, while max_length is used to store the maximum length of a substring found so far. The algorithm iterates over the string using a right pointer. For each character in the string, it checks if the character is already in char_index and if its last seen index is greater than or equal to the current left pointer. If so, it means the character is repeated within the current window, and we update the left pointer to char_index s right +1 to exclude the repeated character and maintain a valid substring. Regardless of whether the character is repeated, we update its last seen index in the char_index dictionary to right. We then calculate the length of the current substring as right left +1 and update max_length if the current substring length is greater than the previously recorded maximum length. By the end of the loop, max_length contains the length of the longest substring without repeating characters. This approach ensures linear time complexity, O(n), as each character is processed at most twice, once when expanding the window and once when shifting the left pointer. This makes it an optimal solution for the problem. Here, we start by importing the necessary Java utilities and defining our solution class. Inside the length of longest substring method, we initialize a hash map called char_index to store the last seen index of each character. This allows us to track where each character was last encountered in the string. Next, we set up two pointers, left and right, to define the current window of the substring we're examining. The left pointer helps us maintain the boundaries of the window, while the right pointer iterates through the string. We also initialize a variable maxLength to store the length of the longest substring found so far. Now, as we begin iterating through the string, we use the right pointer to access each character. If the current character already exists in our map and its last seen index is within the bounds of the current window, we move the left pointer just past the last occurrence of that character. This ensures that the substring remains valid, with no repeating characters. After adjusting the left pointer, we update the last seen index of the current character in the map, and then calculate the length of the current substring. If this length is greater than our current max length, we update max length accordingly. Finally, after completing the iteration through the string, we return the max length variable, which now holds the length of the longest substring without repeating characters. This approach ensures an efficient solution with a time complexity of O(n), as each character is processed at most twice, once when it's added to the window and possibly again when the left pointer is adjusted. The use of a hash map allows us to quickly check and update character indices, making this implementation both clear and performant. To solve this problem, we use a sliding window approach with 2 pointers, left and right. Initially, we set up char_index as an empty dictionary to track the last index of each character, left to 0 as the starting point of the window, and max_length to 0 to keep track of the longest substring we've found. Starting with the first character, at right equals 0, we see a. Since it is not yet in our char_index, we add it with its index, resulting in a 0. The length of the current substring is calculated as right left plus 1, which gives us 1, so we update max_length to 1. Moving to right equals 1, the character is b. Similarly, b is not in char_index, so we add it, resulting in a 0, b, 1. The substring length here is 2, so we update max_length to 2. At right equals 2, the character is c. Again, c is not in char_index, so we add it, making a 0, b, 1, c, 2. The substring length is now 3, and we update max_length to 3. Now, at right equals 3, the character is a, which already exists in char_index and falls within our current window. To ensure we don't include duplicates, we move left to 1 position past the last occurrence of a, which is char_index, a, plus 1 equals 1. We then update char_index to reflect the new index of a, resulting in a 3, b, 1, c, 2. The substring length remains 3, so max_length is unchanged. The process continues for the remaining characters, ensuring no duplicates are included in the current window while updating max_length as needed. In this example, the longest substring without repeating characters is determined to have a length of 3. Now, let's explore another case with the input string s equals b. Again, we initialize char_index as an empty dictionary, left at 0, and max_length at 0. Starting with right equals 0, the character is b. Since b is not in char_index, we add it with its index, resulting in b, 0. The substring length is calculated as 1, so we update max_length to 1. At right equals 1, we encounter b again. This time, b is already in char_index and its last index, 0, is within the current window. To avoid duplication, we move left to char_index, b, plus 1 equals 1. We then update char_index to reflect the new index of b, resulting in b, 1. The substring length is now 1, so max_length remains 1. This pattern repeats for each subsequent b in the string, as all occurrences of b lead to the window being reset, and the substring length remains 1 throughout. As a result, the longest substring without repeating characters here is of length 1. For the input s equals pq, we again initialize char_index as an empty dictionary, left at 0, and max_length at 0. At right equals 0, the character is p. Since p is not in char_index, we add it, resulting in p, 0. The substring length is 1, so we update max_length to 1. At right equals 1, the character is w. Similarly, w is not in char_index, so we add it, resulting in p, 0, w, 1. The substring length becomes 2, so we update max_length to 2. At right equals 2, we encounter another w. Since w is already in char_index and its last index is within the current window, we move left to char_index, w, plus 1 equals 2. We then update char_index to reflect the new index of w, resulting in p, 0, w, 2. The substring length now becomes 1, and max_length stays at 2. At right equals 3, the character is k. The character k is not in char_index, so we add it, resulting in p0 w2 k3. The substring length, calculated as right left plus 1, is 2, so max_length remains 2. Continuing with the remaining characters, we find the substring y starting at left equals 2 and ending at right equals 4, which has a length of 3. This becomes our new max_length. At the end of the traversal, the longest substring without repeating characters is determined to have a length of 3. The time complexity of this solution is derived from how the sliding window technique processes the string. First, we have the main traversal loop, which iterates through each character of the string exactly once. This contributes O(n), where n is the length of the input string. Next, the dictionary operations, such as checking if a character is in the dictionary and updating its index, are performed in constant time, O(1), due to Python's efficient hash table implementation. Additionally, the left pointer adjusts only when a duplicate character is found in the current window. Since each character is processed at most twice, once when moving the right pointer and potentially once when moving the left pointer, the total adjustments for the left pointer are also O(n). Combining these components, the overall time complexity of the algorithm is O(n). The space complexity is determined by the extra memory allocated for the dictionary used to store character indices. In the worst case, the dictionary will contain one entry for each unique character in the string. If the string has all unique characters, the dictionary size will be the minimum of the string length n and the size of the character set, denoted as charset_size. For example, this could be 26 for lowercase English letters or 128 for ASCII characters. Therefore, the space complexity for the dictionary is O(n) charset_size. Additionally, the algorithm uses a few pointer variables, left, right, and max_length, which each require constant space, O(1). Combining these, the overall space complexity is O(n) charset_size, which simplifies to O(n) when the character set size is small compared to n. To better understand the efficiency of this solution, let's compare it with the brute force approach. The brute force method involves generating all substrings of the input string, checking each for duplicates, and then keeping track of the longest valid substring. This results in a time complexity of O(n cubed, as generating all substrings takes O(n squared, and checking for duplicates in each substring takes O(n). On the other hand, the optimized sliding window approach processes each character at most twice, resulting in a time complexity of O(n). In terms of space complexity, the brute force approach uses no extra data structures, so it is O(1), while the sliding window approach requires O(n) charset_size, space for the dictionary. Mathematically, the linear time complexity of the sliding window approach is justified because each character is only added to the dictionary and processed once when expanding the right pointer, and the left pointer is incremented most once for each character. This ensures the total number of operations is proportional to n. The efficiency of this algorithm holds across all scenarios. In the best case, such as when the string has no repeating characters like A, B, C, D, E, F, the left pointer never needs to move, and the dictionary simply tracks each character as the right pointer expands. This results in O(n) time complexity. In the average case, where the string contains some repeating characters, the sliding window mechanism continues to ensure that each character is processed at most twice, maintaining a linear time complexity of O(n). Even in the worst case, such as when every character repeats frequently, like in the string abababab, the left pointer adjusts for each duplicate, but no character is processed more than twice. This guarantees that the time complexity remains O(n) in all cases, highlighting the robustness and efficiency of the algorithm. When solving the problem of finding the longest substring without repeating characters, there are a few common mistakes you should watch out for. First, overlooking edge cases can lead to errors. For example, if the input string is empty, or if all the characters in the string are identical, like AAAA, many algorithms fail because they don't account for these scenarios. It's important to handle these cases to ensure your solution is robust. Another mistake is inefficient iteration. Using nested loops to generate all substrings can drastically increase time complexity to n cubed, or worse, which becomes impractical for larger inputs, such as strings of length 10,000 or more. This kind of brute force approach may work for smaller examples but will time out on larger test cases. Lastly, ignoring the sliding window optimization is a critical oversight. The sliding window or two-pointer technique is much more efficient, and failing to implement it leads to unnecessary complexity, which not only slows down your solution but makes it harder to debug or analyze effectively. Another common issue involves incorrect usage of data structures like hash maps or sets when implementing the sliding window technique. For instance, if you forget to remove characters from the set or map while shrinking the window, it causes logical errors. This might lead to overcounting or skipping valid substrings entirely. Similarly, incorrect updates to the result can throw off your final answer. If you update the maximum length of the substring in the wrong part of the loop, or fail to compare the current window size to the maximum, you might miss important cases, especially when the longest substring appears near the end of the input. These small but critical mistakes can lead to incorrect or inconsistent results, so attention to detail is key. Now, let's talk about insights that are particularly useful during interviews. Mastering the sliding window technique is essential, as many substring problems, like finding the longest or minimal substring, rely on this principle. Recognizing patterns in the problem statement helps you identify when this approach is applicable. Efficient use of hash maps or sets is another critical skill. These structures are often used to track characters for uniqueness or their indices for efficient updates. Knowing exactly when to modify or reset these data structures can make or break your solution. It's also important to keep edge cases in mind. Interviewers frequently include scenarios like empty inputs, single character strings, or highly repetitive patterns to test your thoroughness. Finally, be prepared to discuss trade-offs. While brute force methods can be a good starting point for brainstorming, you should always aim to optimize and explain why your chosen approach is better in terms of time and space complexity. There are several related problems that build on similar concepts, so practicing them can help you strengthen your understanding. For example, LeetCode problem number 3, finding the longest substring without repeating characters, is often the foundation. Other problems like minimum window substring, number 76, longest repeating character replacement, number 424, and substring with concatenation of all words, number 30, are great follow-ups that test variations of substring techniques. Additionally, it's worth considering alternative approaches to solving these problems. The brute force method, for instance, involves generating all possible substrings and checking each for uniqueness. While it's helpful for learning, it has a time complexity of n cubed, and is not practical for larger inputs. This method is best reserved for understanding the problem rather than for implementation in time-sensitive scenarios. A more practical and widely used approach is the sliding window technique. With a time complexity of n, this method ensures that each character is processed at most twice, making it highly efficient even for large input sizes. Its space complexity depends on the character set, such as 26 for lowercase letters. Sliding window is ideal for performance and scalability. Dynamic programming is another option, though it's rarely the best choice for this specific problem. It has a time complexity of n squared and space complexity of n squared, making it less efficient. Lastly, hashing can be a powerful tool, with n time complexity and n space complexity. Hash maps or sets are especially useful for tracking indices or dynamically maintaining uniqueness. Each of these approaches has its strengths and trade-offs, so understanding when and why to use them is crucial for success in both interviews and real-world applications. Great work! We've successfully tackled the longest substring without repeating characters problem. Remember the key insights we discussed, leveraging sliding windows and hash maps to optimize performance. Don't forget to practice similar problems to solidify your understanding. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!